Hi, my name is Steve Murphy with Teledyne LeCroy, and I'm here today at Selig Company in Rochester, New York, and here to introduce to you one of the, actually a couple features on the HDO4000 digital storage oscilloscope. And we're going to focus today on when you're validating a circuit and troubleshooting. There's tools built into the scope that I think you're going to find pretty interesting and unique. So here we've got my source is a microchip 8-bit PIC, and I've got it set up to do a pulse width modulated signal, which we'll lose. And there's also some anomalies happening here, but to get us started, here's the acquisition. I've set up the peak to the appropriate levels, and this is our trigger point right here. We're using channel 1 as our input, and what we're going to do is I could use cursors and start making pulse width measurements, and so that would be manual, useful, but tedious. So this time, though, I'm going to go up, and this time I'm going to use the measure setup. And what I'm going to do is create a table of parameter measurements, and I'll turn on the parameter table right here. We have 8 of them that we can select from here and add to the table. I've got 3 already set up. P2 is amplitude. P3 is frequency, and P4 here is width. We're all using, in this case, the source is channel 1 right now, but they could be any other waveform that's not displayed. To add another one, let's go to P5 and say, let me see, I want to look at rise time, for an example. So we've added that to the chart. So if we stop the scope, we'll do a single shot. These parameters are measuring the last one of the waveform. So frequency, width, and rise, these are all the values on the last feature. And this is amplitude, which is an entire waveform. What is the amplitude across this whole waveform? And it's listed there. The maximum is 5 volts. So what I'm going to do now, though, is I'm going to turn on statistics, and to present this to you, I'm going to clear sweeps and do a single shot acquisition. And I wanted to point out that every feature that we've asked the scope to measure that is listed in this table is being measured. For example, we have 1 amplitude measurement, as I was saying earlier. It's in a complete waveform measurement. And then there are 12 frequency measurements, 12 widths, and 13 rising edges that are being measured. And because I've turned on statistics, I've given you the last measured value as we saw earlier before I turned on statistics. But now I'm looking at the mean of all of these 12 and 13 measurements. And the mean is, let's pick on width right now, the mean is 191 microseconds. And we got the min and the max there is 156 and 227 microseconds. So, and again, this is on 12 different measurements. So if I let this run, I'm looking to validate my circuit design, and I'm just going to slow this scope down and capture a wider time window. There we go. And then now what we're seeing is of all the parameters, we're measuring right now, here we go, 1,500 width measurements, 15 and now 2,000 frequency widths and rise times as well. And of all those values, the mean now, let's pick on width again, 197 microseconds. The minimum, is showing 165 nano, grossly different from the 197 micro, and then the largest is showing 241 micro. So this is our first indication that indeed we have a problem with our circuit. The range of these values for width are not what I like. And even over here, when we look at rise times, we see that the average rise time is 32.6 nanoseconds, but the min is, not bad, 32 nanoseconds. The largest, though, is unexpected at 106 nanoseconds. If I touch this with my finger, or I'm driving this with a mouse too, you have your choice. I'll go back to the touch screen. I'm going to turn on histogons. And what we do is we can see here that this is a graphical statistical display of the measurements. Now we're at 10,000 width measurements, and we can see that most of the, if this is 0 width and that's widest width, most of the values of the measurements are around that 197 microseconds. And we do see off to the left, we do see a very small outlier closer to 0, and the height of that represents the number of measurements that are in that very that small narrow width. So at any rate, we can see now how the data is changing, not just the range. Very useful to quickly show you that indeed you do have a problem with outliers. Look at this, even in the rise time we can see we've got an outlier. We have wider rise, slower rise times than most of the other measurements. So let's dive into that a little bit more. And now we're going to start doing some troubleshooting. I'm going to, right on the front screen here is WaveScan. So I'm going to go ahead and turn on WaveScan. I also have it from a pull-down menu. And what I'm going to do is, I've asked WaveScan to give me not just a display, but actually a listing of every one of the rise times that are in this waveform. This is 49 width measurements, and we have asked WaveScan to turn on and identify the measurement, in this case width, by identifying it in red. And we now have a table that is interactive with a zoom trace, and this is the 34th pulse width. It's 197 microseconds, and it's centered right here. So we can see how that works. And then this is 233.8 nanoseconds. So far when I look at this list, I don't see any outliers. It all looks pretty much around my mean, and I would be pretty happy. But I know I've got some issues going on. Let's say, hey, WaveScan, would you please go ahead and filter this out for me. Please tell me my rarest 5 measurements, please, and show me where they are in the data. And that's what WaveScan is doing right now. Instead of providing everyone, we're providing only the 5 worst case. So that is a tool to help me find it. Geez, let me go ahead and look to see. Oh, wait, I saw one. Oh, there it is. I see a narrow one right here. If I touch that, close this out, and then make sure zoom has been selected, and now we'll take a look at that in more detail, and there it is. So there's that glitch, shorter than the 197 microseconds, which was my mean. So again, this is a troubleshooting tool that helps you identify glitches, or if right now, without acquiring more data, I go ahead and say, hey, go ahead, WaveScan, and show me rise times. And I'll shut off the filter at this point, and we can see all the values of rises. And we do see, oh, wait a minute, there is instead of 34 nanoseconds, we have one that's 105. I am just going to go ahead and take a look at that in closer detail and zoom in on that, and then we can see we have a non-monotonic edge going on there where we did not have a nice clean rise time, maybe from a reflection, an impedance reflection on the circuit. So this is useful tools to quickly identify glitches. The key thing that helps me do this is measuring from the parameter table every occurrence of every feature that we've turned on in the parameter table, and then using statistics shows you the range of values to confirm that you're happy with the performance of your circuit, or to identify problems with the range. Turning on histogons gives you the distribution to confirm graphically how the data is changing and confirms you have an outlier. And then we turn on WaveScan to help you identify and look at all the data, search on the rarest events, and also we can set up a software trigger on any values that are unexpected as well. So you can have it within a range, out of a range, outside of 3 sigma if you would like. So these are all now trigger conditions within WaveScan that help you identify glitches, slow rise times, runts, and things that you did not expect as measurements on your circuit's performance. So thank you very much for your attention. Please call Salig Company for any questions and to find out more details.